When an information system outgrows its physical boundaries, the math required to navigate it has to scale accordingly. Traditional information retrieval algorithms were designed for small, predictable environments, like a physical library catalog, where the collection of documents is coherent, well-labeled, and completely static. The World Wide Web operates on a different logic. It is a massive, continuously shifting node-link graph that lacks any central organizing authority or defined edge. This environment imposes severe engineering constraints. The data pool is essentially infinite, spread across geographically distributed servers, updating at completely unpredictable intervals. Brute force indexing fails in these conditions. A system cannot simply read a decentralized, infinite database from start to finish. Instead, search engines rely on specialized, highly parallelized software pipelines, known as crawlers, to constantly traverse the network. To understand how this mechanism actually works, we have to construct a crawler architecture from first principles. Operating this system requires solving two distinct mathematical problems: prioritizing which pages to download first, and scheduling how often to revisit them to maintain freshness. Building a search engine is an optimization problem, the constant balancing of finite compute resources against infinite decaying data. The process begins with a finite list of starting points, known as seed URLs, or S0. The crawler program takes these seeds, resolves the addresses, and retrieves the corresponding page data from remote host servers. This diagram outlines the general architecture of a search engine. On the left side, we can see the crawler modules acting as the interface between the live web and the internal storage systems. Once the HTML is retrieved, the crawler passes it into a temporary storage bank, known as the page repository. From there, an indexer module extracts every word, creating a lookup table that maps terms to the specific URLs where they occurred. Simultaneously, the system parses the downloaded page to find new hyperlinks pointing to unvisited nodes, extracting those URLs to continue the cycle. These newly discovered links pour into the crawlcontrol module's queue. Because every downloaded page contains multiple new links, this recursive feedback loop creates a bottleneck. The crawler cannot process an exponentially growing queue simultaneously without crashing target servers and exhausting local bandwidth. This introduces a priority dilemma. How can a system determine the value of a node before expending the bandwidth to download it? The solution relies on page selection metrics, mathematical proxies used to estimate importance from the outside, using only the limited data available in the URL itself. The first heuristic is interest-driven selection. This measures textual similarity, calculating the cosine angle between a query vector and the estimated content of the target document. The second heuristic is popularity-driven selection. This approach evaluates importance through backlink density, treating incoming edges from other sites as citations of value, independent of the page's actual text. The third heuristic is called location-driven selection. This evaluates the topology of the URL. The system assigns higher priority to shorter domain paths, URLs with fewer forward slashes, or specific root structures like .com. To make a final routing decision, the system uses a composite algorithm to calculate a priority score, combining these independent heuristics based on specific mathematical weights. Prioritizing the crawl queue is the act of combining these heuristics into a single execution order to maximize efficiency. To verify which heuristics actually work, researchers evaluate them using a framework called the crawl and stop model. The crawler is given a hard budget, K, representing the maximum number of pages it is allowed to download before shutting off. The success metric calculates the percentage of the network's truly important nodes, the hot pages, that were captured within that strict budget. This line graph displays the empirical performance data for different selection algorithms, plotting the percentage of total pages crawled against the percentage of hot pages captured. The straight diagonal line serves as the baseline. This is a purely random crawl, which scales linearly. Capturing 20% of the hot pages requires crawling 20% of the entire web. A breadth-first search, represented by the red line, offers only a marginal efficiency improvement over the random baseline. By contrast, backlink count and PageRank curves shoot up steeply extremely early in the crawl cycle. Popularity-driven prioritization bends the efficiency curve, allowing the system to capture the vast majority of valuable nodes while consuming a fraction of the compute budget. Prioritizing the initial queue is only half the battle. The long-term maintenance of the indexed graph presents a different challenge. Because the real-world web changes constantly, the offline copies held in the local database suffer from index decay. Without maintenance, they rapidly become obsolete. The system relies on a revisit policy, the mathematical model governing how frequently the crawler must check back on a known indexed page. A uniform refresh policy revisits all pages at the same frequency. This method wastes network resources checking static pages that haven't changed, while simultaneously missing crucial updates on highly dynamic nodes. The optimized alternative is the proportional refresh policy. This policy tracks the historical change frequency for each page, lambda, and allocates a revisit frequency, f, that matches that volatility. This diagram outlines the full architecture once more. A dual tension exists. The system must push outward to discover new nodes via the queue, while circling back to update the repository and preserve the integrity of known nodes. The search engine operates as a highly constrained, continuously running graph traversal system, mathematically balancing the exploration of the unknown with the exploitation of the known.